Let's get the recording started. All right. So let's go ahead and talk about motional EMF. So what exactly is motional EMF? You sort of explain to me what exactly it is, or at least as best you can. How's it going, Kevin? Talking about motional EMF here.
So EMF stands for the electron motive force, and it is produced by usually a magnetic field that allows the electrons to flow in a certain direction from a higher potential to a lower potential.
And how does it do that? What exactly causes the higher potential and the lower potential?
The induced magnetic fields, and that magnetic field would be what causes the electrons in a wire to move a certain direction.
So you're saying the induced magnetic field causes the electrons in the wire to move?
Yeah.
Not quite. It's the electrons moving is what induces the magnetic, is what creates the induced magnetic field.
All right.
So what causes the electrons to move in the first place from an external magnetic field? Motional EMF involves some sort of movement through a magnetic field. What causes when you move through a magnetic field?
A magnetic force.
Exactly. Then what happens if you're not moving in a magnetic field?
No force because
Yeah.
there's no velocity.
Exactly. There's no force, there's no velocity. But because we have some sort of metal, or, for example, like a wire, and if we move it through a magnetic field, all those, little charges, technically they're electrons, but we're just going to call, we'll just say they're positive charges, because that's how we define current. We have all these charges in the metal, in the wire, that then there's a magnetic force on them, and that's what creates the EMF, because they get moved due to the magnetic force. Does that make sense? That's essentially the best way of describing what's going on. And honestly, I don't totally understand why he does it this way. He always starts with motional EMF, and then he talks about Faraday's law. Personally, I think it's easier to go the opposite way, because you can derive motional EMF from Faraday's law, and we'll actually do that in a little bit. But so essentially, sort of recap, we have our magnetic field, let's say here, let's say it's coming out of the page. And if we have a wire that enters the magnetic field, if we have velocity to the right and magnetic field out of the page, what direction is the force on the positive charges in the wire going to be? Remember our right-hand rule for magnetic force?
Would it be to the left?
Nope. If our velocity is to the right and our magnetic field is out of the page, we have to be perpendicular to both of those, right? The force has to be perpendicular.
Right.
So it'd have to be up or down. Which one is it?
It would be up.
Is it up?
Yeah.
If you point your pointer finger to the right in the direction of the velocity, curl our middle finger towards the direction of the magnetic field, which is out of the page, your thumb should be pointing downward. You left-handed over there, Kevin?
Nope, I'm right-handed. Did it the wrong way because I thought the magnetic field was the other way.
Yeah.
So, yeah.
Remember, the dot means it's out of the page. It's like, imagine an arrow. You're looking at the tip of an arrow. And the cross means it's into the page. It's like you're looking at the feathers on the back of the arrow as it goes away.
Right.
So let's go ahead and hop into an example problem. So we're going to have a square slab of uncharged metal. So let me actually go ahead and redraw this now. So we'll have our magnetic field. We have a square slab of uncharged metal, so something like that. Side length 5 centimeters, velocity -5 meters per second in the z direction, so it's actually going to be up above. So let me draw our magnetic field, and then we have our slab here. It's going to enter a uniform magnetic field out of the page. So what's going to be the potential difference across the metal slab, and which side of the metal slab is going to be positively charged, and which side is going to be negative? Let's take like 4 or 5 minutes, then we'll talk about it. Usually redraw this like this. It's as it's entering. So like 2 more minutes, then we'll talk about it. How's it going, Nikosi?
I'm good.
We're doing the first question here, A and B. We're going to be talking about it in about a minute or so.
Okay, cool.
We're going to talk about motional EMF and right-hand rules and stuff. All right, so how do we actually go ahead and find the potential difference across the metal slab? how do we find our voltage difference from one side to the other based on its movement into the magnetic field?
Wait, you mean the like the magnitude or like?
Yeah, let's just talk about the
or
let's talk about the magnitude. Let's talk about the magnitude first.
All right.
Direction's easy. It's just a right-hand rule.
Hold on, I'm breaking out the formula sheet.
Well, you didn't already have it open? Hell's wrong with you? Worship the goddamn formula sheet. Simplifies things so much.
You know, I have it saved to my desktop. It's just I have to get to there. All right, so we use epsilon equals VBL.
But that's for the EMF, right? Is that the same thing as the potential difference?
No.
Why wouldn't it be? Why isn't it?
Potential difference, that's basically voltage. I just didn't hear it the same.
Mm-hmm. So you're saying...
Oh, yeah, that's equal to voltage. It's just in my mind, I didn't think it was like potential difference, because I don't know.
Yeah, it's the same thing. Yeah, most people like to think of it as a voltage. In reality, the voltage is, I mean, it's all about a difference between voltages. And so we'd like to, the actual term is potential difference. But yeah, it's a voltage, essentially, across it. And we know we can find it because EMF is another word for voltage, essentially. And we can find it using our formula. Epsilon is equal to VBL. Where V is our velocity, right? And then we have the magnitude of our magnetic field, and we have the length of our side of our square. And we can plug the numbers in. It's like, what, 5 meters per second times 0.3 Teslas times the length of 5 centimeters. You guys can do that yourself. So that's how we'd get the magnitude of the potential difference. And now, which side of the metal slab is going to be positive and which side is negative? How is this potential difference oriented?
The charge is going from left to right, so the greater potential is on the right and the lower potential is on the left.
So you're saying the greater potential is on the right and the lower potential is on the left. So which side is positive and which side is negative?
Positive would be the right side.
And why is that?
That's because the electrons are moving to the left. And,
Are they?
Shoot. Maybe not.
Right hand rule. What direction is our velocity in?
It's downward.
Downward. Fingers curl
Towards us.
out of the page. What direction is your thumb pointing?
To the left.
To the left. Now, is the right hand rule for positive or negative charges?
It's for positive.
Positive charges, exactly. Our negative charges are going to go in the opposite direction.
Completely mixed up the whole.
So it's going to be something like this. We have all our positive charges on the left, and all of our negative charges on the right.
Definitely thinking like chemistry or something. I don't know.
It's in physics, goddammit. Chemistry is just applied physics.
Yep.
Not literally everything you learn in Chem 101 and Chem 102 is literally just applied quantum mechanics. Fun fact. But yeah, so essentially we use our EMF equation, epsilon is equal to VBL, and we use that to find the magnitude, and then we go back and use the right-hand rule to find which direction is going to be the positive side and which direction is the negative side. Does anyone have any questions about this? Tim, were you going to say something a minute ago?
Oh no, you got it. Thanks.
Okay, cool. All right. So yeah, honestly, this motional EMF stuff is really, really just you apply the formula, like, you know, monkey see formula, monkey plug things in, and then you use right-hand rules to find stuff out. So honestly, it's pretty simple. So now let's go ahead and talk about slightly little bit more annoying stuff, and you can actually find that you can actually just start with Faraday's law and you can get to our motional EMF. So what is Faraday's law? Does anyone want to tell me what it is?
It starts with an enclosed loop.
Mm-hmm.
And when it enters, an enclosed loop will, I don't know how to describe it. Try and balance out with changes in like surrounding magnetic field. So like the induced magnetic field would be.
I think you're more thinking of Lenz's law.
Oh, lenses. Okay.
First of all, let's just start off mathematically. What is Faraday's law? It's easier to describe things once we have the formula in front of us, and then we can try to connect our thoughts to what's actually on the paper. Anyone else want to give me Faraday's law?
Is that the integral of B dot dA? Is that the one?
Mm-hmm. And what does that give us?
The flux, the magnetic flux.
Exactly. So we have our magnetic flux is some sort of phi b is equal to our integral of B dot dA through some sort of a, I mean, in this case, we're talking some sort of a loop of wire usually. So this gives us our magnetic flux. We have a magnetic field through a loop of wire, and we have the area, and essentially we integrate the magnetic field over the area, and it gives us the total flux. It's sort of like Gauss's law from back with electric fields, where we had the electric flux, and then this is the magnetic flux. And so now, what is Lenz's law? Kevin, you were saying something about induced imposes, something like that?
Right, an enclosed loop would shoot. I'm just losing the words. But mostly I'm just thinking about the 4 steps that we went over for discussion and like finding out the direction of induced magnetic fields based off of changes to surrounding magnetic fields.
Yeah, I mean, that's basically what Lenz's law is. But then also we want to know, what exactly causes the induced, so we have our induced magnetic fields caused by the what? What causes the induced magnetic fields? What causes magnetic fields in general, usually? How can we create a magnetic field? Think back to like last week.
Would it be some sort of current flow?
Exactly. We have some sort of a current flow. And what causes a current flow in like a wire loop, for example?
some potential difference between 2 points.
Exactly. And what creates the potential difference? This is
Would
what
that be an electric field?
would be that what?
An electric field? Some.
Not quite for this example. We're talking about Lenz's law here.
Yeah, I'm lost on this one then.
We have a current that's created by a potential difference or an EMF. What creates the EMF in a wire loop, for example? Take a look at your formula sheet. You should see some sort of a formula that involves EMF. What causes our EMF is a change in the flux. So we have our flux here, which is an integral of B dot dA. And then if we have a change in flux over time, that generates an induced EMF, which then generates a current, which generates our induced magnetic field, which, as Kevin said earlier, opposes our, or sort of opposes in, quotation marks, our magnetic field. That's our external magnetic field. Does that make sense? Does anyone have any questions about that?
Yeah, I don't know if you just have to read it or understand it, but conceptually, could you go over why that is?
So, is this your first SIPass session you've been to?
Yeah.
Yeah. So this has sort of been a running joke that I've sort of said a few times throughout the semester. Physics, nothing in this class makes any sense conceptually. So nothing really makes sense conceptually, and it's sometimes hard to really find explanations that make sense in most people's heads. And even for physics majors who like me, the only reason I understand a lot of this stuff is because I like numbers. I like math. And for me, I'm able to take a look at the math and see that the math makes sense and works out. If you take 99% of what we do in physics and try to explain it conceptually to a biology major or a theater major, they're going to be sitting there whoosh, right over their head, what the hell's going on? This doesn't make any conceptual sense. But the best way to explain it is I'm just saying that to be there's not really going to be a good explanation. But essentially, as our wire loop here from this first example, let's say this is a wire loop. There was an uncharged metal thing. But
okay.
If this is a wire loop, it's going to enter, and we have our magnetic field out of the page, and our flux is an integral of B dot dA, right? Our magnetic field isn't changing, but the total area of the loop that we're integrating over that's inside the magnetic field is increasing. So the total flux is increasing, and we're going to generate a current, which then generates a induced magnetic field that opposes that change to sort of balance it out. Like I said, it doesn't really make too much sense, but it's the best we've got. And we can use right-hand rules if we just trust ourselves with our practice with the right-hand rule and trust the math. Everything actually works out, and we can solve problems.
Okay, I think I get the concept.
Yep.
It's kind of like if you're holding something heavy and you keep adding more weight, your arm doesn't rip off. Your muscles just kind of tense up to bear the tension until it could no longer give.
Yeah, that's actually a pretty good example. But
Okay.
Yeah, so essentially we have our Faraday's law, which is the magnetic flux, and then Lenz's law is the fact that our induced EMF, the way he puts it in here, is the induced EMF is the magnitude of the change in flux over the change in time. And then he doesn't have it in the formula sheet, but I also like to think about a negative sign here just to sort of remind us that it's going to oppose the change in flux. So let's go ahead and hop into an example. So we're going to have a 2 centimeter square loop of wire. It's going to look something like this. It's going to be traveling 5 meters per second to the right. We have our side length L, and we have our velocity. And it's going to enter a uniform 2 Tesla magnetic field into the page. So this is our section of magnetic field. And our magnetic field is into the page. So first of all, what direction is the induced current in the wire loop going to be? And what is going to be the induced EMF and current in the loop? Don't think about Lenz's law and Faraday's law. Just think motional EMF, our VBL, and remember our potential differences up here. Let's take 5 minutes and we'll talk about this. All right. So how would we go ahead and find the direction and then the magnitude of the current in our loop and also our EMF? First of all, let's start with the magnitude. Let's do B first and then go back to A. How do we find the magnitude of our induced EMF?
So the practical way of doing it would be you add up all the EMFs of all the line segments included, but realistically only one of the line segments has an EMF.
Exactly.
Because let's see.
Start with the left one. What happens with the left one?
It is outside of the magnetic field, so
Exactly. No EMF.
I would zero out right there.
What about bottom and top one?
The bottom and top one, the EMF involves a dot product, a dot product between
Is it the dot product?
Is it the dot product? Yeah. I know it involves a cosine 90, and that's how it zeroes out. If I actually remembered all the bits and pieces of the formula. But
I think your thought process is correct. I'm just going to say you're right, but it's not the way I would think about it. I would think about it with a cross product, but it still ends up being zero.
Right.
But I don't want to ruin your thought process, and since you have it correct, you're good.
All good.
So then that just leaves the right side.
Yeah. And now it'd just be VBL.
Exactly. So our EMF is equal to VBL. And so then what would be our induced current in the wire?
I would be the EMF over the resistance of the wire.
Exactly. Right. It's just Ohm's law. I is equal to V over R. In this case, V is our epsilon. With VBL over R. If I can write a good-looking R to save my life. So now, how do we find the direction of the current? Is it clockwise or counterclockwise?
It's counterclockwise.
And how do you get that?
All right, third time's a charm. Right hand rule.
And
So,
talk me through your process.
Fingers pointing to the right. Your middle fingers into the page, and your thumb is pointing up. And since there's no other EMFs on any other wire segments, that direction is like the most dominant one, I'd say.
Mm-hmm.
In most cases, because like there's other cases where like, you know, there's two EMFs going in the same or opposing directions, and then you have to choose like the winning one, I think.
Sure.
But anyways, that's just counterclockwise.
But yeah, exactly. So right hand rule, pointer finger to the right, middle finger into the page, thumb pointing upward. That is the force on positive charges. Positive charges get pushed upward, and then obviously up and then around the loop. Counterclockwise. So now, let's go ahead and do that whole part again, but we're gonna start with Faraday's law. So we're just gonna go through it together. So first of all, we'll start with Faraday's law. We have the flux, phi b, whatever, is equal to our integral of b dot dA. So what is b dot dA, dot product? How does that simplify?
The B would be constant. The dA would be what's changing since the wires.
A few steps ahead here.
Oh, okay.
Let's just get rid of the dot product first.
Right. So it'd be B dA cosine theta.
Exactly. And what's the angle between them?
That I'm having a little trouble with. Would dA be... The A in dA would be area, right?
Yes. What direction is the area vector for an area?
And that's in the same direction? Or opposing directions? I don't know. It's parallel.
It's parallel. That's what I'm looking for. Essentially, if we have an area, let's say something like this, let's say a flat surface, the area vector is parallel to it. Or, sorry, perpendicular to it. It goes outward. Whether you want to define it as up or down really doesn't matter. It's just, in general, we define it as if it's a 3D surface, it's going to be outward. But apart from that, it really doesn't matter how we define it. So, magnetic field is into the page, and our area vector we'll define it as into the page, perpendicular. So the angle between them is 0, cosine becomes 1, so it's just B times dA. And then you said magnetic field was constant, right?
Yes.
So we have our B, and then we have the integral of dA. What's the integral of dA?
That would be the length times what would our variable be for the width? Just W?
Sure. Let's call it W, or let's call it X. Let's say the total length of the side that is inside the magnetic field. Essentially, the integral of dA gives us our area, the total area inside the magnetic field. So we'll call it B, A, which is B times the length here times the width that's inside X. So that is our magnetic flux at, whatever time, depending on, how much of the loop is inside the magnetic field. So now, how do we get the induced EMF? What's the induced EMF as the function of the flux again?
That'd be right up there, the equation, the second equation we have up there.
Exactly. It's our change in flux over change in time.
Yep.
So we have epsilon is equal to our d dt of BLX. Is our magnitude of our magnetic field changing over time?
No.
Nope. So B can come out. Is our length here of the wire loop changing over time?
No.
Nope. So it's just BL times dx dt, the total amount of the loop that's inside the wire, inside the magnetic field. What is our change? What's our dx dt?
Velocity?
Exactly. That's just our velocity. BLV, or VBL, however you want to put it. I think from our formula sheet, it's VBL. Yep, we have our magnetic field times our length times our velocity. That's just our motional EMF that we've gone ahead and we've derived it from Faraday's law. And so now Lenz's law, how do we find the direction? How do we find the direction of our induced current?
Do we start with the sum of all the segments?
Let's think of it more of what direction is our flux in? Our B dot dA, our integral of B dot dA. What direction is our flux in? It's going to be the same direction as our magnetic field. So that's into the page. Is our flux increasing or decreasing?
The flux is increasing.
The flux is increasing, and it's into the page. So the change in flux is increasing into the page, so the change in flux is into the page. So then, Lenz's law, we have our little negative sign. Our induced EMF is going to oppose the change in flux. So because the change of flux is into the page, let's go ahead and take our thumb, point it out of the page. What direction do our fingers curl?
That's counterclockwise.
Counterclockwise, exactly. That's how we go ahead and use Faraday's law and Lenz's law to derive what we had from our induced EMF.
Wait, so question. The change in flux, is it always going to be opposite to the B field?
In this case, the change in flux is in the same direction as the B field.
Okay, I'm confused on that.
Essentially, we have our magnetic fields into the page, right?
Yeah.
And so our flux is going to be in the same direction as the magnetic field. So it's into the page. And then our flux is increasing over time because X is increasing as we're moving to the right. correct?
Yeah.
So because our flux is into the page and the magnitude is increasing, we're saying our change in flux is into the page. If our loop was here and it was leaving the magnetic field, then X would be decreasing. Flux is into the page, but because it's decreasing, the change would be out of the page. Does that make sense?
Yeah, it does.
Yep. Essentially, we're just keeping track of what direction the flux is in, and then whether it's increasing or decreasing. From that, we get what direction, in quotation marks, the change in flux is. It's literally just keep track of your right-hand rules, and you hopefully, I mean, this, I'll admit, this is the main part of the class where a lot of students get negative sign errors on their flip it homeworks. I'm sure you guys have been experiencing that quite a bit because it's sort of hard to keep track of what direction things are in because there's like 4 right-hand rules going on. Does anyone have any more questions about this?
Yeah, it's still kind of sketchy to me. So, okay, if an object is going into the field, because more of the object will be going into the field, the flux increases, correct?
Exactly.
Okay. And when the flux increases, there's going to be an induced current because of the induced EMF.
Yes. And what direction? What direction is that current in, or what does that current do?
The current would normally go in the direction of the force generated, induced by the B field, correct?
And what about relative to the induced? What about the direction relative to the change in flux?
Yeah, that's the part that trips me up. So, all right, let me try and attempt it. So, okay. Okay, no, I'm just completely blank with that.
It's going to oppose the change in flux. So we agree that the change in flux is into the page, right?
Yeah.
So take your thumb, point it in the opposite direction, out of the page. What direction do your fingers curl?
Clockwise. Sorry, counter.
Counterclockwise. That's the direction of our induced current. It's going to go opposite of the change in flux. Because our induced magnetic field from the current is going to go out of the page to counteract the change in flux. Does that make sense?
Yeah, it clears it up a bit more.
You're lying. It doesn't make sense. And that's fine.
First time.
Yeah. And this is one of the things where it's hard to wrap your head around it conceptually. And I think you were a little bit more comfortable with finding the direction of the force, right?
Yeah, I've got that down.
Yeah, from the first part where we just used emotional EMF. If that works for you, use that. Don't worry about Lenz's law right-hand rule directions.
Got it.
Opposing. Just use whatever works. For me, I prefer Lenz's law. And I prefer the opposing, point your thumb in the opposite direction. But use whatever works.
Got it.
So let's go ahead and hop into the last little bit here. So the wire loop is going to be traveling here, and it is going to fully enter the magnetic field. What's going to be the induced EMF in our wire loop once it's fully in the magnetic field?
Would that be just 0?
And why is that?
So for I keep forgetting the names of the laws, but for integral of b dot dA, none of the conditions are changing, or parts of the integral are actually changing.
Mm-hmm.
So the induced EMF would be 0.
Yep. Yep, exactly. So our flux is B times our area, which is B times L times, in this case, X would be the full length inside the magnetic field, so BL squared. Neither B or L is changing. So EMF is change in flux over change in time, which is 0. So now we're going to have our loop sit inside our magnetic field, and our magnetic field strength is going to decrease by, 0.5 Teslas per second. Who cares about the numbers? So what's going to be our induced EMF and current in the loop, including the direction? Let's take 8 minutes, then we'll talk about it. I'll give you a hint. You're going to be forced to use Faraday's law here. All right. So how would we go ahead and find our induced EMF and current in the loop? Can't quite use our fallback of just motional EMF because there's no motion here, right? So what do we start with? We're going to have to start with Faraday's law, right?
Yep.
So
that would be change in magnetic flux over change in time. But
and so let's start with getting the magnetic flux itself.
That's integral of b dA, but that would zero out, right?
Would it?
Yeah.
Also, welcome, Mohammed. We're going over the last problem here. Why would it zero out?
B would be a constant in this situation, right? And then you're left with, oh, right. We have to simplify the dot product.
Yeah. But we know that's
1.
Exactly. So then you said B is a constant, right?
Yep, B is a constant. And then the integral of dA would be just area.
And then what's our area of our loop here?
That's 2 centimeters squared? Or... Yeah.
Yeah. Or in this case, I'm just going to call it L squared.
L squared, okay.
So we have BL squared. So now how do we get our induced EMF?
You put that over change over time.
Yep, exactly. It's the change of the flux. So it's ddt of the flux, which is BL squared. Is L changing as a function of time?
No.
No, but our magnetic field is. So we have, this becomes L squared times dB dt. And we have the dB dt, so then we can go ahead and let's actually go ahead and plug numbers in for this one. Why not, right? So we have 2 centimeter squared loop of wire. So we have L is 0.02 meters squared times dB dt, which is 0.5 Teslas per second. We're not going to worry about magnitude yet. We're just going to worry about magnitude. We're not going to worry about direction. So we get an induced EMF of 2 times 10 to the negative 3. And what's the units for EMF?
Isn't that just volts?
Yep, exactly. It's just a voltage. So then if we want to get our current is going to be our EMF over the resistance in our wire, right? So then we divide that by our 100 ohm resistance, and we get a current of 2 times 10 to the negative 5 amps. All right, does that make sense? So now, the fun part. How do we find the direction of our current? Remember, what direction is our magnetic field in?
Was it still into the page?
Yes, it's still into the page. So our magnetic field is into the page. So what direction is the flux? The flux is the same direction as the magnetic field, right? It's also into the page.
Okay.
Is our flux increasing or decreasing?
Decreasing.
Our flux is decreasing because our magnetic field is decreasing. So what direction is the change in flux in?
Negative.
So what direction would that be in? If our flux is into the page, what direction is our change in flux if it's decreasing?
It's also into the page.
Is it?
Well, I know that if it's
If we have a ball that's, let's say, 10 feet above the ground, we can say its location is positive, right?
right.
If it's falling downward though, is its velocity positive or negative with respect to the ground?
That would be negative.
Yeah. If it's above the ground, but it's traveling downward, so its change in height, or in this case its velocity, is negative. And in this case, our flux is into the page, and the magnitude of it is decreasing. So the change in flux is out of the page. Right? So what direction is our induced current going to be in?
Counterclockwise.
Why is that?
That would be basically I'm just gonna be looking at like one side of the loop. So for the right side, my fingers would curl. Shoot. All right, I'm thinking the opposite. Counterclockwise. Wait, yeah, it would be clockwise.
Mm-hmm.
And fingers would curl into the page. Thumb would be down. I think that's it.
So wait. Take me through your whole process. How are you? So you're talking about the right side of the loop?
Right. Like, I know that
You're trying to
like
think about
change in flux. That's also like a direction. Like,
Mhm.
you know, it'd be into the page, and I just follow the curl of my fingers to like go clockwise, but like usually I go for like one side and then follow along with the inside of the loop. I don't know how to describe it, and do the right hand rule that way too. But
You're doing something interesting. I mean, because the easiest way I'd say to do it is change in flux is out of the page. Point your thumb in the opposite direction into the page. What direction do your fingers curl? Clockwise.
right.
But what you're doing is you're trying to do like some sort of a magnetic force calculation on each part of the wire. Is that what I'm hearing?
Yeah, basically, I would orient it around the inside of the wire. So, if I chose the right side, I'd say, my fingers would have to point in the direction into the page, and then the current would be, along my thumb, pointing down.
But
That makes sense.
we don't have any movement though, right?
Oh, right. But I don't know. That's just how I'm thinking of it.
I mean, if that
But, like,
works,
yeah.
if it works, it works. But I'm gonna be completely honest, straight up with you. I don't know what the hell you're doing.
Right.
But yeah, easiest way: change in flux out of the page, point your thumb into the page, curl your fingers.
Right.
The same way with our example from earlier, where if we tried to do it without right hand ruling magnetic force. Change in flux in this case was into the page, so we curl our fingers out. Or point our thumb out, curl our fingers. Does anyone have any questions about this? All right. Well, in that case, that's going to be pretty much it for today's session. Hopefully this helped out a little bit. Honestly, the easiest way to get comfortable with this is just practice, practice, practice. And we'll have more practice on this later today. Later this week, so tomorrow. Tomorrow, going into your quiz on Friday, there's going to be more practice on Lenz's law and right-hand rules and Faraday's law and getting comfortable with it. So, if that's it, no questions. Thanks, guys, for coming. If you guys haven't filled out the attendance form, it's in the announcements text channel. If you could do that, that'd be greatly appreciated. Thank you. And have a good day, guys. Thanks for coming.
All right. Thanks.
Thanks for the help, man.
Mm-hmm.